So welcome to our next section, next major portion of our course. We're going to now be looking at inferential statistics. And this is either Chapter 8 or Chapter 6, depending upon which curriculum you're in. So, inferential statistics, remember, that is when we take a sample and we apply it to the population. And what we're going to start with is we are going to take a sample statistic, the mean, x bar, and we're going to use that to estimate an unknown population parameter, the mean, symbolized by mu. Okay, so remember these symbols give us different. So this is the symbol for the mean if it's in a sample, so sample mean, and this, the mu, is the symbol we use when we have a population mean. And in a population it's called a parameter, in a sample it's called a statistic. So just applying all these vocabularies we've used and learned. The broader topic of what we're talking about is called a confidence interval, and we're going to see how that is. So we're going to calculate what a population mean might be using confidence intervals. And this first step, we're going to assume or have knowledge of the sigma, which is a standard deviation of the population. Now you might ask, how can we, if we don't know the mean, how would we know the standard deviation of a population? Sometimes it is known. We will look at ways when it's not known, how we proceed from there. Okay, but today we're going to assume we know what the standard deviation of a population is, and that's going to help us estimate what the mean could be. So there are two types of estimates. The first one is called a point estimate, and we can use the sample mean, x bar, to estimate what the population mean is. One problem with this, though, is it's a particular value, and remember, as we take different samples, it is likely we will get different, each sample will have a slightly different mean. Some might be the same, but so that mean could be different depending upon the sample. So if we just use a point estimate, we might not, there's going to be some error. And so one way to incorporate that error is to use an interval to figure out that there's a point, but there's going to be a plus or minus, kind of like what we've been doing with the standard deviation. Also, we could call this a standard error and a margin of error. And we'll see how all that relates as we go through here. But using an interval, we get a range of values from above to below, and we can gives us a more robust interval, a confidence. We get confidence in that interval. That's why it's called a confidence interval. Okay, so first of all, we start off with some critical values. And where do those critical values come from? Well, I was a little bit ahead of myself here. Remember when we were doing distributions, and then our last set of stuff, we would go to the normal curve. One of the things we could do with this, we're in a standard normal with a mean of 0, a standard deviation of 1, is we could find an interval where a certain percentage might be. So this one we're looking for between 2 points, right, a plus or a minus. Let's go with a 90%. So we want 90% of the values, and what we're going to find is that between negative 1.6 to positive 1.6, rounded to 1 decimal place, or if we go to 6.4, 2 decimal places, right? Between these two values, 90% of the data is there. And those become our critical values. So let's define that a little clearly. The critical values are the negative z and the positive z, up here listed that x is between, and they separate the sample statistics that are likely from the sample statistics that are unusual. And let's look at a graph here. in general, these values are separating. The shaded region is the likely region, the white or lighter regions, the beige, is the unusual regions. And we're going to see what we do is we define it to be whatever they give us. Usually common ones are 90%, 95%, 99%, 98%, but those may change depending upon how much confidence we want that the interval does contain the mean. Okay, so for a 90%, you'll see here we had 90%, we get 5%, right? Because 90% minus 1 is 10%. 5% are in the little tails, we call them, the white regions down here. And the z-scores are negative 1.645. And we look up here, negative 1.64. The 4 gets rounded up, 645. Went to positive 1.645. So these numbers, these critical values that are listed here, we're going to be able to find those with our calculator using the distribution right here. Okay, so we're going to be able to do those. Notice that, since we're going to be using things like a 90%, you could memorize these or write them down so you wouldn't have to look them up. But whenever you need them, we can go back to the calculator and find them right here. Okay, so doing a 90% confidence interval. And that means in our tail here, and these numbers we'll see later on as we move forward, this would be 0.05 or 5% would be here, and 5% would be in this tail. 90% is up here in the shaded region. And again, 1 minus 90 gives us 10%. So 10% is in the tails, and the tails are equally on each side. Okay. So that's what we're going to be using for confidence intervals. And these numbers that we're getting here, we'll see how those apply. What about a 95% confidence interval? Well, all we do is we change the 0.9 to 0.95. Now, when would we use a 90%? When would we use a 95%? Primarily, we'll see in our homeworks, they tell us what kind of a confidence interval we should use. If you're doing research, you will decide from your research committee which one to use. Again, standard one is about 95%, but sometimes we might want to go with a 90%. It just depends upon the accuracy of our data, how much and how much we feel that we can trust it. Okay, and so look at here at 95, I have to do the execute, but that's going to be about negative 1.96. We'll round it to 3 decimal places because if you go too much further out, everything gets rounded up anyway. So 1.96, and we'll see here 95% confidence interval, 2.5% on each side, and our z values negative 1.96 and positive 1.96, so plus or minus 1. Those are our corresponding z-scores or critical values. Okay, so you see how that works. Again, sometimes you just want to remember these, but remember we could write those down, but we can also have access to calculating them with our tool here. So this came from these numbers right here. So we're seeing that we're starting to apply things that we've learned in our last sections. And that's how statistics, we always build on the knowledge we've gotten. Okay. So questions, and we'll do a few examples. So it's a 95% confidence interval. And if we want to do a 99, we could do that, whatever you want to do. We're also going to see that we've got some built-in features in here that help us not have to memorize too much. So what is sampling error? Remember, this was one of our last sections that we did just before the exam. It's the difference between the point estimate and the actual population parameter value. It's the sampling error. So for the mean of a population, the sampling error would be the difference between the sample mean and the population mean. Oftentimes the population mean is unknown because, again, we're dealing with a population of sometimes massive sizes. We can't actually get all the data. However, the sample mean varies from sample to sample, so it's something that's going to have some variation in it. So we want to calculate what the margin of error is, and that's going to help us build our confidence interval. And we think of the margin of error as the maximum error or estimate of the error tolerance, and that's part of how much error are we willing to accept. The larger the confidence interval, the larger the error, the potential errors, right? The greatest possible distance between the point estimate and the value of the parameter is estimating. So we're going to use the letter E to stand for margin of error. Again, we're going to see how our calculator will calculate this for us, but there's also a formula. And two things that are required is that the sample has to be randomly generated for all this to work, and the population, remember this from before, the population has to either be normally distributed, or if it's not, the size of the sample has to be greater than or equal to 30. So if it's normally distributed, it could be any size. If it's not normally distributed, or if it's unknown, we need a sample size of at least 30. And in that case, our error will be this formula. And remember, we could use the standard deviation of the sample. Let's go with blue. That's this one right here. However, if the population standard deviation is known, then we can use that and estimate the sample with the estimating factor of the square root of n. So this was from our last section that we did, and then we multiply it by that critical value that we're going to come up with. So this is our formula. However, we're going to see, again, we have a feature where confidence intervals will be calculated for us by the calculator. But this is the main. In fact, let me clear this out. This right here is a formula we're going to be using throughout the rest of this. Okay. So let's find the margin of error. We're asked to, again, most questions will tell us what the level of confidence we want. So they're telling us to use a 95% confidence level. So we know we can use these values, but we're going to see, we'll be able to calculate this as well. To find the margin of error for the mean number of hours spent on required athletic activities by all student athletes in a conference. So that's the, so all is referring, that's telling us that's what the population is. Use the given sample and assume the population standard deviation is 2.4. What given sample? Well, it's right here. Okay, so this was a sample, and we can see 1, 2, 3, 4, 5 down, 1, 2, 3, 4, 5, 6, 7, 8. So this sample has a size of n equals 40. We would need to calculate its mean, right, for this sample, but what we're going to do is have some technology that already did this for us, so that we know that the sample mean is 19.9. Now, how do we go about building this confidence interval? Let's go back here. This is under the statistics. Remember, there's these 4 parts: statistics, regression, we'll get to that later, distributions we've used. Now we're going to use inference. Okay, and we will use tests not too long. It's another section, but what we're working on now is intervals. And what we're going to do is, we know one mean. We're given a mean, and So the steps I have labeled here, so when you go into Canvas, you can click through here, and remember I've got highlighted. You go to interval, you go to, you go to inference, and then intervals, and then one mean. Okay, and then we're going to click OK. What we want is the Z interval for this one. We will do T intervals and talk about that later in another section that we'll do, but we want Z intervals. And we could input the statistics, which is what we want to use, or you could use a data set. So if you didn't know the mean, you could actually enter all this data and it will calculate it for you without having to jump out separately. But since we have the statistics, we're going to input them. Okay, and again, we'll click to the next one. What do we put in? We've got the sample mean is 19.9. We have the standard deviation of the population was given to us as being 2.4. I always ask, how do they know that? Well, we just assume that they somehow know that. A lot of times that is from a previous study. The sample size was 40. Again, we've got 40 pieces of data here, so we put that in. That's important. And the confidence level that we want is 0.95. So that we enter all that. Okay. And we're going to click on OK. We'll move down to next. And what it has calculated for us is the margin of error, which is right here, 0.7434. And we've got the standard error, which let's go to the next one. I'll show you how the formulas could be used to calculate that. So we've got this information here. And I guess if we go one more, we're going to come back to this as well. We actually get the confidence interval is given to us. So we're going to see how. So notice we just had to enter this information. It calculated it all for us. I'm going to back up a step. But had we not, the way we would have gone through doing that by hand would involve the formulas. Okay. So first of all, how can we do this? Well, first of all, we know the sample is greater than 30, so we could use it regardless of whether the population is normally distributed or not. The z-score that applies to a 95 is 1.96. Again, we didn't actually have to calculate that, but it's they brought it up for here, right? The z critical score, part of the calculator's feature. And then so we've got this sort of setup. What we're getting, we put in our values. Now, if we would have used the formula to calculate it, we would have taken those values and we would have got 0.7. Notice we did get 0.7 for our margin of error. The standard error, if you take this part, which we've calculated before, 2.4 divided by square root of 40, you're going to get this as 0.379, the number exactly that we've got here. So here's our standard error. In case you ever need to do it, it's part of the formula. So if we could take these and we could calculate this, which we've got given to us right here. Okay. And we're able to say we're 95% confident that the margin of error for the population mean is about 0.7 hours. And we're going to see how we can apply that to a confidence interval. Okay, so again, standard error got calculated for us. It shows for us. We maybe don't really need that, but what we're going to use is this margin of error, and it's calculated for us. Okay, so sometimes I'll ask, what is the margin of error? We've got it right here. To build the confidence interval, and notice they've got to kind of do some more, we take the sample mean and subtract the error. We take the sample mean and add the margin of error. Okay, so we've got two sides to this. Again, in our calculator, that is done for us in the next step. Notice they take the mean and add and subtract the margin of error, and then they give it to us up here. Okay, so let's go and see that next step. To calculate this, again, we've already got it, but what they would do is they're going to take the sample mean, which we inputted, and they're going to add, subtract the margin of error, and they get 19.2 and 20.6. Again, here's a picture of our confidence interval. We were able to calculate that, or a calculator did it for us, these two endpoints here. Okay, and you see the plus or minus right here. So we've got all that information, and all we had to do was input it, and it takes care of the formulas that are all built in here. Okay, so as we do questions, know how to use this tool. It's going to make things much nicer. You won't have to memorize all the formulas, except for one last thing that we're going to do, which is finding the what sample size we might need. So again, we notice we could write this out as an interval on a number line, but that's exactly what the calculator does for us. Some of the other calculators don't show the visual. The nice thing with this calculator is we can also, if we wanted to change like to a 90% confidence interval, maybe we think, oh, maybe I need less. You could just backspace and you could do a 90. You could do an 85%. So notice the confidence interval is getting shorter, but then you have less confidence that the mean would actually be there. It's only 85%. But maybe you want a 98%. So these are all here, and nicely, once you've input them, you can get whatever interval you want, or that is available for us here. Okay. But definitely we can make this statement. We've got 95% confidence that the population mean number of hours spent on required athletic activities is between 19.2 and 20.6 hours. And again, we built it off of samples without having to go and find from all the population. Okay, so let's do another example, and we'll see how we can, from the beginning, just construct a confidence interval. And I'm going to back up to the beginning where we start with interval. So a college admissions director wishes to estimate the mean age of all students currently enrolled. In a random sample of 20 students, so this is going to be probably important, the mean age is found to be 22.9. From past studies, the standard deviation is known to be 1.5 years, again, and the population is normally distributed. Now remember, that is important because our sample is only 20. It's not 30 or more. So we need the population to be normally distributed, and we're told it is. We're asked to construct a 90% confidence interval, and again, the problem will give us this. We can do all of this, so we're going to walk through this, and then we will see how the calculations could go. But notice we just need to come over here to inference. So again, wherever you are on your calculator, just come down. It's going to be here in the menu. We're going to go to intervals. We're doing one mean today. Again, we'll use some of these other ones as well. And we're doing a z-interval. We're going to input the statistics, and the statistics we're going to use are the sample size, which is n, so n equals 20. We've got from that sample, so this is x bar, this is the mean from the sample, and then we've got the standard deviation from the population, so this is sigma here, and then we know we need a 90% confidence interval. Okay, so we'll input all this stuff. 22.9 from the mean we were given. The standard deviation we're told is 1.5 years. The sample size is 20, so we'll enter that. And the confidence level is not 95, it's a 90% confidence interval that we want. We'll click on next. We've gotten our margin of error, but what there was a question. constructing a confidence interval. Again, sometimes these numbers are in between, so we can see if we rounded this would be a 0.6 margin of error. If we go on, we've actually got our margin, our confidence interval for us right here. And what we're going to see is we just needed to put in our data, and we've got our confidence interval here. Otherwise, you would have to go through all these steps in calculating. Using n equals 20, we entered all this information. Now, we didn't have to come up with this critical value because it was built in, and if we back up, we see the calculator gave it to us. So we don't have to memorize that. It was given to us and then used. Oops. Go back here. By hand, if you were doing this, you would go through this calculation to get the margin of error, which again we had back here. Margin of error is point. We had it more accurately, but rounded it would be 0.6 approximately, right? And then you would take the mean, you would subtract the margin of error on the left endpoint, and the right endpoint you would add it. Again, we would just click enter, and we get those two values, 22.334, so we round it to 3, and 23.5, because that 4 gets rounded up, 23.5. So we've got those values just by using our tool. We've got a margin of error, and then we get the confidence interval. And that's how we do that one. Okay, and notice a lot of times they want us to set it up. This calculator's already given us that interval, a picture of it on a number line with the plus or minus. Okay, so we've got that built in. So as we work to, in the homework you'll be doing several examples of these. The thing we want to say is this is not a probability. Right, we're taking a sample. The mean of the population, it exists. It is a number. It's not going to change on us. So this is just a confidence that we can be 90% confidence, have confidence that 90% of the intervals that we could take a sample from will contain the actual mean of the population. So what does that mean visually? Well, let's take a look here. If we were to go and take 10 samples, what we would find with a 90% confidence interval, what we should find, is that 9 of them, at least 9, because remember, so out of 10, they include this unknown actual mean of the population. Notice there is one right here that does not contain the actual mean. However, all the others do. So these 9 here all cross over the actual mean of the population. Again, this is all theory. We still do not know with 100% certainty what that mean is, but if we take enough samples and we follow this the theory of statistics, which has been tested out again and again, we are going to have a 90% confidence that the population mean is within these parameters that we're coming up with, okay, within these confidence intervals. And notice sometimes we might get a sample that exactly the mean is the same as the population, okay, but we're just working with this theory. And again, in statistics, we don't always have to be exactly sure on something, the exact value, as long as we know what that we're willing to accept a certain level of error, we can be close enough. That's what I like about statistics. And some people will say that's why statistics isn't math, because it's not an exact science, but we don't need exact in most of our daily activities. We just need to be close enough in the ballpark. So the last part, we're going to need to do a little bit of calculation, and that's because sometimes when we're doing a study, we know what we want to do, but then we've got to say, hey, what size of a sample do I need to estimate that? Because remember that error is affected by the sample size. And if we, you know, if we don't have the right sample size, our error will be either too large or too, it's okay, I guess, to be small. But what we do with this is we're going to use that formula, and we will have a confidence level that's given to us. So given a confidence level. And they're also going to need to give us what size error they're willing to accept. Okay. We will then be able to calculate the minimum size needed to estimate that population. So there'll be a few questions like this. What we end up doing is, if n is, we calculate it and it's not a whole number, then we round it up to the next whole number. Okay, because you want to make sure you have it. You don't round down, because then you'd be just a little bit short. If the standard deviation of the population is unknown, we can use the estimate of the sample standard deviation, as long as we have 30 members in our sample. Okay, so those are some things. So what we do is we start with this formula, and we do a little bit of algebra. Now, we won't have to do this each time, because once we do it, you're going to see over here that's something you would put in your notes. But I just want you to show is all we're going to do is we're going to solve for n. So we're going to get n by itself. So how would we do that? Well, maybe multiply both sides by the square root of n. Okay, so that means that we have the square root of n times e equals z sub c. Remember, that's that critical value, the z value, times the standard deviation of the population. And then we would divide both sides by the error. That would cancel out. And then since this is square rooted, we need to square it. So we would take this and we would square it. So n is equal to this, and I'll just click over here and notice that's how we've got to this formula. Now from this point on, what's a good thing to do is probably put this into your notes, your page of notes that you get for your exam. Okay, so we're going to get that, and we're going to work with this. We'll do an example. Okay, so notice we will be given E, we're given the standard deviation, and we're able to get this value one way or another, again, from either the inference or from going back to the distribution. Okay, so let's look through an example, and then we're done with the lesson for the day. So the researcher in example 1 wants to estimate the mean number of hours spent on required athletic activities by all student athletes in a conference. How many student athletes must be included in a sample to be 95% confident, so we're given that the sample mean is within 0.5 hours of the population mean. This here is our acceptable error. It's our margin of error. So 0.5 plus and 0.5 minus. Remember from that, we were given the standard deviation is 2.4 hours. That's from the population. So what we do is, to calculate n, we need the critical z for 95. If you don't remember it, which is okay, remember we can come back here, and you could just put it in here as 0.95. And then when you do that, it's going to be given to here, the critical value is going to be 1.96 rounded up, right? Or if you are someplace else, remember we can also come back to distributions, and we can find it this way, 0.95. So I'll just kind of start over here, make sure that's okay. Make sure you have the between two numbers, and that you put in 0.95. Okay, and you see 1.96, negative 1.96 to 1.96. Okay, so that's our critical value for z. And now back to the story. So we put in 1.96, times the standard deviation of 2.4 divided by the error that we're given, which is 0.5. And then we're going to square that. Okay, so to do all of that, we go back to our main calculator, and we can just enter this with the parentheses, 1.96 times 2.4 divided by 0.5 in parentheses, actually in parentheses there. We're going to square that, and we get our number of 88.5. We want to round that up to 89, and not just round it up. Even if it was 88.1, 88.01, we're going to want to get a sample of 89 to have that kind of an accuracy. Okay, and when you're doing a study, you need to do this in advance. Because you know, if you only collect 40 and then you do all your calculations, oh wait, that's not a good enough estimate. Our margin of error is too high. Well, then you have to either go out and do another sample, but better to do it in advance. Okay, and I remember doing research, or my professors would tell me, do this calculation first, and then you go out and you collect. That's how many sample. That's what your sample size needs to be, at least 89. That's okay if it's bigger. If it's bigger, our margin of error will be smaller. Okay, and then I'll just show you. Let's so 89. Remember, it's right there. What we would do here is the same thing they've done. They just plug it in. They get the 88.51, which is exactly what we got, and you round it up to 89. So. The sample that they had of 40 is not good enough for this. They need 89, so they got to go collect another 42 students. So you could do something like that, but they might make you start all over and say, go get 89. So that's why it's important to estimate what size of a sample you're going to need to have the level of accuracy that you want. And that brings us to the end of this lesson. We're going to look at other ways of building confidence intervals when we don't know the standard deviation of the population, and in other settings. Okay, thank you.